Next up, I wanted to do another example. This one's going to be a little bit trickier. We actually have some terms that we cancel out in those steps 4 through 6. I also wrote it a different way. Find the potential function for a vector field. And so when you read it this way, you just have to remember that potential function is some little f, so that capital F is the gradient of that little f. And this is also just a function of two variables. We did 3 before, but it's fine to do 2. We just stop after 2 variables because we run out of components of the gradient. So in this case, we need to solve for x plus y plus x is our vector field capital F. And we want to set that equal to a gradient vector df dx, df dy. And I don't do df dz because there's not a third component here. So taking that vector equation, we can represent it as a system of 2 equations where we need df dx to be equal to that first component x plus y, and we need df dy to be equal to that second component y plus x. And then we rearrange this using integration so that we can solve for f, which is the thing we want. So f from the first equation should be the integral of x plus y with respect to x. And then we have that k1 that could depend on y, and we wouldn't necessarily know it from that integral. Or, looking at the second equation, f could be the integral of y plus x integrated with respect to y. And in that case, there might be some unknown constant k2 that depends on x, and we couldn't know it from this integral with respect to y. So next up, we have to integrate these functions. Oops. So first up, we have the integral of x plus y with respect to x. So the integral of x is 1/2 x squared, and the integral of y with respect to x is y times x. Hopefully we're pretty comfy with that kind of thing after all of chapter 12. The second integral is integrating y plus x with respect to y. So the integral of y with respect to y gives us a 1/2 y squared. And then the second part, integrating x with respect to y, just gives us x times y. And when we do this part, we go ahead and ignore that k1, k2, because we don't necessarily know what they are at this point. And now we go through and we do the crossing out part of the process. So my first integral gets to stay the way it is. 1/2 x squared plus yx is my first integral, and I don't bother with it at all. Then when I get over here to my second integral, what I do is I check the terms and see if they recreate anything from the first integral. And if they do, I cross it out. So my first term, 1/2 y squared, that's different from what I got at first, 1/2 x squared or yx. So that can stay. But then the second term, xy, is the same as yx. So because I've already seen this term before, I cross it out. I don't include it when I move forward with the process. And then if this was a function of 3 variables, I would go ahead and do the third one, and I would check against my y and x outputs to see what needs to get crossed out. And now I add up everything that I have on this line right here that's not crossed out yet. So from left to right, I've got 1/2 x squared plus yx plus 1/2 y squared. And I don't add on that xy because I crossed it out for being similar to something I already found. And that would be my answer. Because I'm a little picky, I prefer to write that 1/2 x squared plus 1/2 y squared plus xy. but it's the same thing. And so real quick, just sort of reminding us about this discussion we had down here on the previous slide. I want to point out that now if we look at f, we can tell that k1 was that 1/2 y squared, and k2 was that 1/2 x squared. So k2 depends only on x. It doesn't show up when you take derivatives with respect to y, and it doesn't show up when you integrate those derivatives with respect to y. And same with 1/2 y squared for derivatives and integrals with respect to x. But, for example, for our x variable, 1/2 x squared and yx both show up in the integral and show up in the final f. The way this case kind of differed from what we did previously is that in this example we had xy show up in both integrals, but we only added xy to f once. So when we took our integrals, we found 2 occurrences of xy, but we only use it the first time we find it. The reason for that is because it depends on both the x and y variables. And so it's going to show up in both coordinates of the gradient vector. And since it shows up in both components of the gradient, when we sit here and integrate the 2 components of the gradient, we're going to sort of like double count that function if we don't remember to cancel it out. And so to sort of convince you that this is necessary, let's go ahead and compare. Let's say we did f the way we say we should, where we cancel out that xy, but let's also think about a case where we forget to do that and we hold on to both. And let's calculate the gradient, which should return us back to the capital F we started with. So if we take the integral, or the gradient of 1/2 x squared plus y squared plus xy, our gradient has derivatives with respect to x and then y. I'm going to get from 1/2 x squared an x. From 1/2 y squared, I'll get nothing. And then from xy, I'll get plus a y. I'll even, to be extra clear, I'll do like x plus 0 plus y. And then when we do our derivatives with respect to y, the derivative of x squared, oh, that's how you make that go away, that's cool, is going to be 0. The derivative of 1/2 y squared is going to be y. And the derivative of xy with respect to y is going to be x. And so, just like we wanted, this gives us x plus y, comma, y plus x. That's the gradient we wanted, so we know that this is the correct function. Instead, if we did this without canceling out that xy, we would get x plus 0 plus y for the first 3 terms, because that's all the same, but then we would have an extra y. And for the derivatives with respect to y, we would have 0 plus y plus x for the first 3 terms, because they didn't change, but then we would have an extra x. And so that would simplify to x plus 2y and y plus 2x, which is different from the function we started with, so we know that something went wrong there. So we know that's incorrect. So the takeaway here that's important is that we only need the first occurrence of xy to fully recover that f. And we need to be careful to cancel or cross out, I think is the word I used before, so I should stick to that. We need to be sure to cross out those repeated terms when we're calculating our integrals and adding them all to f. Oh man, I messed this up. We do need to be careful to cancel because we do this by crossing out the repeats as they appear. Sorry to everyone who took those notes with me as I wrote it. I'm going to read it. Maybe you have the ability to erase or just write below. We need to be careful to cancel or ignore repeated terms from integrals, and we accomplish this by crossing out repeats as they appear.